So today we're going to talk about representational function as power series. Last time we talked about power series, we actually went over this very simple power series we have, right? We got to remember that one, 1 plus x squared plus x cubed, right? We can write it as a summation sign. Now notice that this here is x to the 0 power, x to the first, x to the second. Every chain it has this pattern, x to the n power, and go from 0 to infinity. Because the first one here is x to the 0 power. That's also a geometric series, right? You can remember. Why is it a geometric series? Because what? From one term to the next, we keep on multiplying with x, right? So the x over here is like a common ratio, right? It's a common ratio. So we know geometric series converge if and only if the absolute value of the common ratio is less than 1, right? Okay. So since the common ratio here is x, so this geometric series over here converge if and only if the absolute value x is less than what? Anyone? Less than 1. Yeah, less than 1. You got it. Okay, so less than 1. And for geometric series, when the common ratio is less than 1, it converge, and we can actually find out what does it converge to, right? So for every geometric series, when it converge, it's going to converge to first term divided by 1 minus the common ratio, right? In this case, the common ratio is x. What's the first term in this one? It's 1. So if this one converge, which means it satisfies this, what does it equal to? Equal to first term, which is 1 over 1 minus the common ratio here is x. So that is equal to 1 over 1 minus x. Okay. So even though I have infinite many terms over here, basically it actually, if x is between -1 and 1, then it's actually equal to 1 over 1 minus x. So for example, if x is say 2/3, so 1 plus 2/3 plus 2/3 square, etc., then it's just equal to 1 over 1 minus 2/3. Okay, so we cannot add up all infinite many terms. However, we know that as this series here go on like this, it's going to approaching to 1 over 1 minus x, whatever this x here is. The x here has to be between -1 and 1. Okay. Now, so last time we actually go from this series over here, right? And then we found this function over here, right? So we say when the x over here is between -1 and 1, this is equivalent to x between -1 and 1. Then this series here, this infinite series over here, is equal to 1 over 1 minus x. Now today we're going to go backward, okay? Now we're going to actually give you a function, something like this. And I'm going to ask you to find a power series, something like this, to represent that function within the interval of convergence. But first, let's try to get a feel of this function, 1 over 1 minus x. If x is between -1 and 1, when x is 0, it is 1. So it's right here. This function f is the wave function, this wave one right here. I go like this. We go like this. As x getting larger and larger negative, it's getting closer and closer to 0, the y value. Now, if you take the n partial sum,
when n stop at 2, you get 1 plus x squared.
so you're going to get this. This is S2. 2 here correspond to the index of that. So the S2 is not the sum of the first two terms. Basically, is the sum of when this n over here stop at 2. S2 will be this. So you sum all the terms all the way until the index here is the same as this one. So S2 is 1 plus x squared. And it looks like this. So it's this curve over here. This one over here. It's a parabola. Part of a parabola right here. And for S3, so what's S3? S3 is going to be this. You add one more term. So x cubed. So that's S3 right here. And then the S3 over here is, they didn't put it over here, but you get the idea. So they take more and more term of that power series. So S2 go like this, S5 go like the blue one, S8, and then S11, you take 11 term. You can see that from -1 to 1, as the number of terms increase, the n partial sum, as of that, is going to be closer and closer to this function. Okay, to that one over there. That's the sum of the function. It's the sum of the series. Okay, like that. So as n increase, the n partial sum become a better approximation to the function. The function is 1 over 1 minus x. Then the more term you get, see, you get 2 term, 3 term, 5 term, 11 term, etc. And you see the more term you get, and that partial sum is going to get closer and closer. You look at the graph, get closer and closer to the graph of this function over here. So that's one way to see a series, right? You look at the series, what does it do? So over here, you can actually see. So the n partial sum getting closer and closer to this sum over here. Okay, now let's take a look at this. Last time I told you guys, you want to remember this result. This is an important result to remember. And the way that you can try to remember this is this. If you can write it as 1 over or number over 1 minus a quantity over here. So that means that you can write it as a power series if the absolute value of that quantity is less than 1. If that absolute value of that quantity is less than 1, I can express this as a power series. So everyone can tell me, what can I write this function as according to this, a power series? Can you come up with a power series for this? Well, remember the x here is the common ratio, right? So this is the common ratio. Whatever you subtract here corresponds to this common ratio, okay? So the first term will be this common ratio to the 0 power. So you will have 1, right? And then plus, what's the second term? Second term will be that to the first power, right? And then the next term here will be what? That to the second power. And then continue in this pattern. Okay, and then that to the third power. Okay, whatever that is. And if I put that in the sigma notation, so that will be the summation side. You don't want to keep on writing this, right? You can write it out to get a feel of how the series look like. However, we want this concise notation for the series, okay? So what should I write over here? That will be the common ratio, right? The x over there, this x over here. So in this case, it's this one over here, this quantity over here. So that quantity to the what power? To the n power, yeah. And n go from 0 to infinity, right? The first one here is to 0 power, that to the first, second, and third, etc. So this suggests that if this quantity here, the absolute value is less than 1, you can actually express that as this power series like this, right? As an infinite series like this. So keep that in mind. So when we're given a function, you can try to relate the function and put it in something related to this form. So you can write it as a power series that way. Now let's do our first example, example 1. I'm going to ask someone to read this. Can I ask Antonio to read this sentence? Yes, very good. So we're trying to find the interval convergence. Remember last time we called that I, right? So last time we say that interval over there, sometimes this, sometimes that, okay? Within the interval convergent, then the series is going to converge, right? Something like that. So we're given a function, okay? Look at this function. It is 1 over 1 plus x squared here, okay? Now they want you to express this as the sum of a power series, okay? So I'm trying to relate this. Can I write this in the form of 1 over 1 minus a quantity? Can I put it that way? Yes. I saw you nodding your head. Okay. So if I put it that way, then what should I put inside that parenthesis? Negative x squared, right? So you can put negative x squared there. So we can put this as 1 over, that is negative x squared there. Okay. So 1 minus x squared. So I make it larger for you. Okay. So you put it that way. Okay. So that's the idea. Now once I put it that way, notice that this is the common ratio, right? Is that the common ratio? It's the common ratio for the geometric series, right? For the geometric series. So we can write this in the power series. Okay, what should I put over here for the power series? Last time we talked about that. If this is equal to what? Yes. So it is whatever that common ratio there, right? And then to the n power. And go from 0 to infinity. Okay. So the common ratio is negative x squared. So we have that one. So we were able to write that power series for that one. Okay. So isn't that bad, right? Okay. But let's clean this up a little bit. Okay. Now for power series, usually you want this, remember for power series, you want it to be in the form of like a Cn times either x minus a to the n power like that, right? So you wanted you want to separate this coefficient with this x to some power, okay? So let's separate this, okay? So what should we do? So that's equal to n go from 0 to infinity. This is negative x squared, so we can take the negative 1 to the n power, and then x to the what power? X to the 2n power, right? X to the 2n power. So we can put it that way, right? Okay. So this is actually in the general form for power series. So this is the coefficient, and this is the part that has this power of n. Okay. So that's the power series representation. Okay. So this is what they call the sum of power series. Okay. That is what they want. So the sum of our series is this one right there. Okay. Sum of power series. But when you're looking at this, you kind of don't quite get a feel of this. How about we write this out turn by turn, just to get the feel of how it looked like. Okay. Okay, let's write down the first couple term. Okay. How do you get the first term? You will substitute the first index in it, right? So substitute 0 in here. What do you get? What's the first one? Negative 1 to the 0 power is positive or negative? Positive 1, right? X to the 0 power is what? is 1, right? So the first term will be 1. Okay. How about you get the second term? What's the second term? Yes. So that will be minus x squared. Basically, is the, remember from one term to the next, well, we start with 1. 1 is actually the first term. In this case, this one here is actually the first term, right? 1 is the first term, okay? And then from 1 to the next, you keep on multiplying with negative x squared, right? Okay, so the next one here will be what? Plus x to the 4. I have a hard time decide what color to put this. Okay, anyway, plus x to the 4, and then what? Minus x to the 6 plus x to the 8 minus etc. etc. Right? Okay. Okay, so we got the power series and we write it out turn by turn to get a feel of how it looked like. Okay. But we also ask to find the interval convergence. Okay. Remember this equal to this, there is a condition. You can write this function as this power series. This power series converge even only if the common ratio here, the absolute value is less than 1, right? Okay. So it converges when the absolute value of negative x squared is less than 1. So we're going to solve for x. We want to see what kind of x satisfies this so that we can find the interval convergence. Because that equal to this, even only if this. Even only if the common ratio is, the absolute value is less than 1. Okay. Solving this, how do you solve this? So that is what? Well, the absolute value of x squared is just x squared itself, right? So it's the same as x squared is less than 1. So for x squared less than 1, x is between what and what? Negative 1 and 1. So we have x is between negative 1 and 1. Okay? Or it's the same as absolute value x is less than 1. Okay? Something. Okay? Okay. So now we got this. Okay, let's got this. X is between negative 1 and 1. That's the interval of convergence. Okay? Because when x is between negative 1 and 1, then the power series is going to, this power series is going to converge and equal to this function over here. Okay, because geometric series converge even only if the absolute value of the common ratio is less than 1. So the interval convergence, we can get the interval convergence by solving this to get the interval convergence. So we get negative 1 and 1. So the interval convergence is from negative 1 to 1. Okay. Now, here's the comment here. You could have determined the weighted convergence by use of ratio test. Now, what we have done last time, right? We had done last time use the ratio test to find the interval convergence, right? But then we had to also test the endpoint, etc. But then it's not necessary because we have a very good series, which is the geometric series here. Okay, geometric series converge even only if the common ratio, the absolute value is less than 1. So you don't have to go through the ratio test to get it. Okay, so for power series, you can go ahead and try to solve that, set the common ratio, the absolute value is less than 1, and then solve for x, then you can get the interval convergence. Okay. Okay, that was example 1. Any question over here? So in this problem, okay, so in this section, we're giving a function, and then we try to find a power series representation, and then we find the interval convergence by solving this inequality, setting the absolute value of the common ratio less than 1. Okay, now the next one over here, example 2. Find a power series representation for this function. Now, let me rewrite this function in this quotient form. Okay, this is the function, right? It kind of looks like the one that we have. So the goal here is, can I write this, relate this with 1 over 1 minus a quantity? Because if I can relate that with that, so I know that is equal to that common ratio to the n power and go from 0 to infinity. So providing that the absolute value of that is less than 1. Okay, so our goal here is to try to relate this. Can we relate to this? Now, one way to relate this, okay, so one way to relate this is this. So we can try to first write this as 1 over, okay, now I have a 2, right? Notice that there's a 2 plus x over there, right? So how about we can take out this 2 as a common factor. Then this part over here, I will have 1 plus x over 2. Okay. Now, this might not be the one that you think in your mind. You will say, why do you want to do this? Let us do it first, and then we'll see the other way, okay? So the book do it this way. I think there's a reason. I'm going to tell you a reason first, later, okay? So you have this 2 over here. You want to take out this 2 as a common factor. So then you can get a 1 over here. Okay, so you can get a 1 over here. So insert the 2. Then after that, what do we do? Any idea? We can take this 1 over 2. And then for this part over here, you can write as 1 over 1 minus what? We just set negative x over 2, right? Negative x over 2. Okay, we got it. Okay. So that way, this part over here is exactly like this. Then we can express that as that geometric power series, right? Okay. Then we say, what do I do with this 1/2? What do we do with it? Well, it just put it in front, right? Just put it in front of the power series. Just put the 1/2 in front. Okay. So 1/2. And for that part right there, you can express it as a power series. What should I put as a power series right there? Yeah, negative x over 2. Okay, whatever that. Okay, so put it there. Okay, and then to the n power, and go from what? From 0 to infinity. Okay, and go from 0 to infinity. Okay. Now, if the 1/2 in front bother you, you can go ahead and multiply this in. Okay, multiply that in. So it looks like the power series that you see before. So if you multiply that in, what do I get? Okay. If you multiply this 2 inside, okay. But first of all, let's think about what happened to this, okay. So when you have this is what? It is negative 1 to the n power, right? And times what? X to the n power, right? Over 2 to the n power, Okay, good. So that part is this. Now, when you multiply this 1/2 inside, the only part it's changing is this in the denominator, right? This 2 will remain the same. So this will be, what do I put over here? So you have -1 to the n power times x to the n power, and then over, okay, over what? 2 to the what power? N plus 1 power. You got it. Good job. Okay. So this is the power series that we're looking for. Okay. Now think about this. So this is the power part, the power of x. This part here, those are the coefficients. This is like those are like the Cn, remember? Okay. So those are the kind of like the coefficient. Okay. Coefficients C1, C0, C1, C2, etc. And then this is the power part. Okay. So that's the power series. Okay. Any question for this? Okay. But let's finish this. Okay. When you find the power series representation, you also want to find the interval convergence. So for all of those are geometric series. Then you can go ahead. How do you find the interval convergence? You set the absolute value of the common ratio to be what? Less than 1. Okay, less than 1. So I'm going to set that less than 1, which is, this is the common ratio, -x over 2. Okay, let's just keep the same kind of that. Okay. So I'm going to set that to be less than 1. Okay. The absolute value is less than 1. Solving this, the absolute value of x is less than what? 2. Yes, -x over 2. That is less than 1. So you multiply both sides by 2. So absolute value of x is less than 2. Okay, or 2. So you should put a 2 over here. Well, if absolute value of x is less than 2, x is between which two numbers? -2 and 2, right? So it's going to be between -2 and 2, not including the endpoint, because geometric series, when the common ratio equal to 1, it diverges. Okay, so you don't even need to test the endpoint. Okay, so the interval convergence will be this. So interval convergence is from -2 to 2. Okay, so you found the power series representation of this function, and when x is between -2 and 2, you can actually represent it by this power series. So what does it mean? So that means that if x is between -2 and 2, so for example, say -1.5. If x is between x is -1.5, if you put -1.5 here, and you keep on adding every term, that actually sum up to this 1 over 2 plus -1.5. Isn't that amazing? You have so many, even many terms, but then it added to the simple number there, right? Okay. So as long as x is between these two numbers, this infinite series will be equal to that. But what about outside? Is what outside of this? No, they don't agree. They don't equal to each other. Okay. So this only works when x is between -2 and 2. Okay. Outside of that, they're not going to equal. Okay. Okay. Question. Now, how about some people say, can I this looks like not your way to write this, relate to this, right? So what's your way to relate this? So let's try this one over here, okay? So 1 over 2 plus x. So what's another way to relate to 1 over 1 minus this? Can you guys think about it? It's not in the book, but let's just go through this and see. So you can also put this as 1 over 1 minus what? Take it x and then minus 1, right? So you can actually take this as a common ratio. Isn't this a little bit awkward, isn't it? Right? Yeah. So you can actually write this as a power series. And this part over here, you have this, whatever you have here. So this is negative x minus 1, and then to the n power, and go from 0 to infinity. Okay. Now, if I put it that way, I say, wow, isn't it much simpler? But there's a reason they do the other way. Okay, let's finish this. So if I want to simplify this a little bit, okay, so you can take the negative side, so negative 1, and then to the n power. And then in here, what do I have? I have x minus x plus 1, right? Is it x plus 1? X plus 1? Okay, to the n power, right? And then you might say, wow, isn't that this one looks simpler? Okay, that's the reason. Okay, I'm going to ask you, what is the center? What's the center for this power series? Yeah, center at so Leo say negative 1, right? Yeah, because x plus 1. So x plus 1 is the same as, if you write it as x minus a number, right? So x subtracting this, let's use a different negative 1. So the center is negative 1. That's the center. That's the center there. So this is a power series center at negative 1. Okay. What about this power series over here? What's the center of this power series? The center of that. So if you write this as x minus a number to the n power, right? So that is x minus, that number over there is going to be 0. The center of that is going to be 0, right? Center at 0. So center, a lot of time, I think they wanted to have a power series center at 0. And that's the reason they go down this route. Okay. So if you go down this, you get a power series here, center at 0. But if you do it this way, this power series here is not centered at 0. Sometimes we like it, but the reason they do this way is you get a power series centered at 0. Okay? See? Okay. So with center at 0, you got when x is between this and this, that's equal to that. Now what about this one? This one here also have the interval convergence. Okay. So you would just take the absolute value of negative x minus 1, which is the same as x plus 1. Okay. And you set that less than 1. Solving this inequality, you should get x plus 1 is between negative 1 and 1. So then x is between which two numbers? X is between negative 2 and 0. So if you write that function expressed by this power series, then the interval convergence for that one is different. It is from -2 to 0. That's the interval convergence for that one. Okay. So which means that for any number between -2 to 0, like for example, negative 1.9, then you can put that negative 1.9 here, and this power series over here will be equal to 1/2 plus negative 1.9. Okay, so within this interval convergence, you can pick any number that the power series equal that. Okay, so they have different interval convergence. Okay, but this one centered at -1, this one centered at 0. Okay, so that's the reason to do that. So if you want to get the power series centered at 0, so maybe try this way. So you take out this whatever number you have here as the common factor, so you can get a 1 here. So then this part here will have will be the common ratio over there. Okay, do you guys got the idea? It's a little bit, at first you might feel a little bit, but that's the way to do it. Okay, and then afterward you can distribute, take this one and multiply it in, and you get that. Okay, now let's look at this example 3. Yeah, you test endpoint. Why? Can someone tell me why? Because for geometric series, if the common ratio is equal to 1, what can we say? It diverge, right? So geometric series converge if and only if the common ratio, the absolute value is strictly less than 1. Strictly less than 1. If the common ratio is 1, it's going to diverge. That happened to geometric series. Think about geometric series. You have, for example, if the common ratio is 1, right? Say you have this A, so the common ratio is 1. Then you will just keep on adding A. Would that convert? It's different. Okay? So this one here is going to diverge. If A is positive, it diverges to positive infinity. If A is negative, it diverges to negative infinity. So geometric series converge even only if the absolute value of that is less than 1. If it's equal to 1, which is at the endpoint, it's diverge. So you don't need to test the endpoint. Okay? Because it's a special series. It's a geometric series. The endpoint is going to be convergent. Does that answer your question? Okay. All right. So this is a good thing about geometric series. You don't need to test the endpoint. The ratio test, you need to test the endpoint. Okay. Yeah, that's a good comment, good question. Okay, try the next one. Find a power series representation of this function. Again, do you think you can relate this? Okay, let me rewrite this. This is x cubed, x plus 2. Can you relate this with 1/1 minus a quantity? Can you relate it to that? Well, it's certainly we don't have a 1 over here, right? We have an x cubed, but it is okay to have that, right? So we can take this x cubed. Okay, so we can take this x cubed over here and then multiply with, put it on the side, okay, and then multiply with what? 1/x plus 2. Then for this part here, you can relate. This part over here, you can relate to this, right? Okay. So you will have, okay, Okay, let's finish this one. So you have x cubed. For this one, do we already have the power series for this function? Example 2, right? So from example 2, so from example 2, we already did this, which is, let me copy that down. That is -1 to the n over 2 to the n plus 1, then x to the n, and go from 0 to infinity. So we already got that one. Example 2. Okay. Then what are you going to do with this x cubed? Can we multiply that in? Right? We can distribute and multiply that in. Okay. So multiply this in. We're going to distribute. So distribute. So what do we get? The only part that's changing is what? The power on x, right? Okay, so the other part here will be unchanged. So it's x to the n and then plus 3. Okay. And go from 0 to infinity. So at first you might think it's a lot of work. However, using the result that we already have from the last example, all you have to do is just multiply this x cubed in to get the power series right here, right? Okay, what about the interval convergence? What do you think about this? What's the interval convergence? What's the interval convergence for this one? Do you guys remember? From negative to 2, right? So this one will have the same interval convergence. Why? Because if this one converge, multiply with x cubed will also converge. Okay, so you have the same interval convergence. This one here is just this one times x cubed. If this one converge times x cubed will converge. You can only it. Okay, so you have the same interval convergence because you got it from this part here from the last one. Okay. Okay, so there's a note over here say it's legit to move x3 across the sigma because it doesn't depend on n. See here, the n is an index, right? So it is legit to move this in distribute, right? So every term will multiply x cubed. So it's okay. 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 Any other question? Okay. Now another way to write this series is this. Okay. Well, do you see the difference between this one and this one? This one here, you see it's n plus 3. This one is just n. Okay. But then they change the index over here. So how do they change the index? Okay. Do you want to know how to change index? Okay. So you want this part here to be a single variable n. Okay. So how about we call that m? Okay. Let's call the m over here. So let this to be called m. So change variable. So we let m to be n plus 3. Okay. Then that series over there, okay, it's going to become, this part here will be x to the n power. Okay. And what about this one? This is a -1 to the n. But from here, we relate n with m, right? N is equal to what? N is equal to m minus 3, right? M minus 3. So you can put m minus 3 over here. M minus 3 over here. And over 2 to the m plus 1. What's the m plus 1 there? M plus 1 is equal to m. So you add 1 to this. So that will be minus 2. So you have m minus 2 right here. Now, when n equal to 0, m is equal to 3. Oh, no. When n equal to 0, m is equal to 3. So when I change the index here to be m, the first index will be 3. So m is going to go from 3 and then to infinity, which is the same as this one. Now you might say that this is m minus 3, they use m minus 1. It doesn't matter because negative 1 to the m minus 3 is the same as negative 1 to the m minus 1. Why? Because the difference is 2. Differ by 2. Okay? So negative 1 to that power, they have the same sign. Okay? If one of them positive, the other one is positive. If one of them negative, the other is negative. So these two are actually equivalent. Okay? So this is another way to write this. And the interval convergence for that series is the same from negative 2 to 2, like that. Okay? Does it make sense to you guys? Okay, good.